Hi, this is Dr. Jones again. Now we're going to go through a few pieces of Chapter 2. We are not going to try to go in depth. I got 17 slides here, including this title slide, and I'm just hitting the highlights. I'm giving you 2 weeks to go through that chapter and look at it, and hopefully the discussions I have here plus your reading will help you as you basically do a review primer on probability and statistics, because that's what this is really all about. What do we mean by probability? So there's a variety of different ways to look at it. The objective approach, which looks at the data that we actually have with observations, and you can take a look at like probability of the event, number of occurrences that it's actually happened versus number of times that you've tried to get it to happen. So, you know, it's a sample size, but it still leads to probability. Otherwise, you have things that are on the logical side. How often could something happen, and how often would you know that something could happen? So, you know, you can logically figure out that if there are 13 cards marked with spades and there are 52 total cards in the deck, then your probability is going to be 1 out of 4 that you would draw a card that had a spade on it. Or flipping a coin with a head and a tail, the chance is 50-50 that you're going to get either one of those two sides, 50-50 that you'll get a head, 50-50 that you'll get a tail. So that is one way to take a look at probability, either how much you actually do observe something happening or how much you can logically figure out that it could happen. Then there's the subjective approach, and that would be where you are not using real data, but you are it is real data, but you're not using observations. What instead that you're using is so there's just not, you know, the same focus on data that you have with the first actual, you know, the observational process. In this one, where you actually have numbers, well, you can have some numbers here because you can, you know, say, well, 57% of the people believe this, that, or the other. Well, that's great, but it's not the same thing as if you were observing the number of tin cans left along a street. That quality of data is not the same as when you say 57% of people believe this, that, or the other. The opinion, it's good, but it's a subjective kind of probability. Now, given that I said that, that does not mean it's a poor measure of probability or likelihood that something is true or could happen. It just means you have not been able to do observations of things. If you were to go and try to do the objective approach to say people's support for a certain initiative, what you would do is you would observe the number of people actually voting for a certain initiative, or the number of people that are giving to a not-for-profit organization, and that would approach doing the objective approach out here. It's still not quite exactly the same, but it would be much closer to an objective approach than doing opinion polls or experts' opinions, which are very good, but there's still opinions out there, and so it doesn't have that same quantitative accuracy. But I'll tell you this, even these right here, if you didn't know that say somebody had spiked a deck of cards, or that they had messed with the heads and tails and weighted a coin, something along those lines. The concept here of understanding, well, there's one head and one tail, and it's got a 50-50 chance. That's what you would think, a logical method of doing it, but the actual observation might prove that that's not true, because they had fooled you. And even when you have actual occurrences, and if you had a tried and true coin and it was fine, and it had one head and one tail, you might, in 100 flips of it, not even approach 50%. You could, because it is just probability. You could have 75 heads and 25 tails. I mean, that's a possibility. Now, what you would assume is that if you had 100 sets of 100 flips, that you would approach the 50-50. But simply doing it 100 times, there's any number of reasons why you might not see a 50-50 split out there, or even close to a 50-50 split. Now, we're using Venn diagrams here to talk about another concept, and that is the idea of probability, considering things that are mutually exclusive and things that are not mutually exclusive. So if you flip a coin and it's a true coin and you have one head and one tail, you would assume that A is the number of observations, or the probability of getting flipping the coin and getting a head, and B, flipping the coin and getting a tail. But the reason you can do it this way is because whenever you get a head, you do not get a tail. You understand that. You can get a head, but not a tail at that same time. So when you look at a Venn diagram, they don't mix, because you can't get a head and a tail. Even if it goes on its side, it's not a head or a tail. And we know that unless it's falling in water or glop or something like that, it's not going to fall inside. It's going to land on the table, and it's then going to be a head or a tail. It may go wrong, 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 but it's going to be a head or a tail. And with that in mind, then those two circles don't mix. But if you have in your second, the figure 2.2, if you have chances that A and B could occur together, that it's not necessarily mutually exclusive, then you can have some mixture of those probabilities, and as opposed to what 2.1 has, which is A plus B, and those being the only possible options, that A plus B is 100% in terms of probability. Then figure 2.2 shows that A plus B is not 100%. What you have is the probability of A, the probability of B, and the probability of A and B. And those three things together are 100%. Now, how can something be A or B or A and B? Well, just take a look at the weather outside. And there are times in the winter that I've seen where it is snowing and raining at the same time. It doesn't happen very often, but just at certain points it might rain and snow at the same time. And so while normally you would say, well, it could be sunny, it could be cloudy, it could be snowing, it could be raining, it could be, any number of weather combinations out there. I have seen it where it was both raining and snowing, and so you would not say they are mutually exclusive. And there's many other things that you would see in this world where mutual exclusivity is not the norm. And so you would not assume that you just need to add those two separate probabilities up, but there are many, many options out there. Now, Bayes' theorem talks to us about the idea that what you thought could happen before, such as here, might actually not be the truth, and that things you learn then could change your ideas. Now, we're not going to get really deep into this. I don't want to do that. But let's take a look at what you do see here on this slide. And in this case, you have what we thought were the prior probabilities. So let's assume that we have a pack of 52 cards that we pull out of a deck. Okay, so we open the box, we draw out the cards. We've got 52 cards, and we get ready to just pull them out and start looking for some probabilities. But then we have some new information that comes in. And the new information that comes in would come in from my daughter, who says, I lost the 8 of hearts last week. The dog ate it. There's only 51 cards in there. Oh, new information. So now my probability's changed. I've lost an 8, so there's only 3 8s instead of 4 8s in the pack. And I've lost a heart, so now there's 12 hearts instead of 13 hearts. So I haven't just lost the 8 of hearts, I've lost one of the 8s, and I lost one of the hearts as well. And it's all wrapped up in one card. Well, now I have what they call posterior probabilities. There are changes made based on new information coming in. And we see this all the time, where they will do polling on political campaigns, and they understand what propositions up and down numbers have been, and they poll somebody. They poll a group of people 1 week before the election, and they get a certain set of numbers, and then 1 day before the election they get another set of numbers. And so if they're trying to predict what election day numbers are going to be, the closer you get to actual election day, those numbers are going to be better than what you had before. You would revise your ideas about it. Well, the same thing is going to be true here. If we threw a set of 2 die, a set of dice out there, and we started getting really weird numbers, then we might wonder if something had happened to those dice, something along those lines. So if you wanted to look at a general form of Bayes' theorem, no, I'm not going to read all this text. This is already in your book. But by and large, this is how you would try to compute out those new probabilities. The idea that knowing now new information, what is a certain probability, and what changes might there be, and can you compute what those new potentialities are once you have certain data, and might be able to revise just because of the data. If you didn't know that a pair of dice was loaded or shaved or whatever, could you figure that out based on the data that you gathered and how it varies from what you would expect if it was 2 normal dice? Other revisions out there, that's exactly what we've been talking about. Is there a chance that you could revise those ideas based upon that information coming in? Or should you get other new information and then make other revisions? I know it sounds confusing. It's really not. We do this all the time. You look at your speedometer, you look at your gas gauge, and you believe that you get 29.5 miles to the gallon or 32.5 miles to the gallon or whatever it is that you get. You believe you get a certain amount of gasoline, miles per gallon of gasoline, and then you realize that your gas is going down faster than not to. And so the chance of you being able to make it to your destination without having filled up has just dropped, because you're using fuel quicker than you had before. And that's all this is. That's all this is. Using that new information to make newer and better decisions in the future. Random variables versus other kinds of variables. A random variable says, as it says here, a new real number to every possible outcome or event in an experiment, so anything could happen. So within whatever the parameters are that you're setting. So if you said that you were going to ask a group of students what their ages are, you know that you're not going to get negative ages, and you probably won't get over 100 just from the likelihood of somebody who's over 100 being in your college class. But it could be any number of it, and it's not just that they're 18 in 35 days and 47 minutes and blah, blah, blah. You can round it off to 18 years, and that's fine. So, but at any one time, pulling a person out, you don't know necessarily that that person's going to be 18 or 22 or 47. So there's some level of randomness out there. Now, discrete random variables are those that you know are like a heads or a tails. When you flip a coin, you get a head or a tail. You don't get 1.5 heads or 3/4 of a head and 1/4 of a tail. You don't get that kind of stuff. So what you're looking for is, in a discrete, that there are specific numbers or observations that come up, whereas with a continuous random variable, you pour yourself a glass of water, it might contain 2.783469 cups of water in that glass. Not just 1 cup or 2 cups or 3 cups, but there's any number of continuous numbers that are possibility. As we look at probability distributions, we're just glossing over this part here, but for discrete random variables, you have people, and we're not looking at half people or 3/4 of a people, and a certain number of problems or certain scores, etc. You still will have some distribution wherever that mean is going to be. And so a table with those discrete variables might look like this. And you might, in your observations, have found, as they did here, that you had 10 5s, 24s, 33s, 32s, and 10 1s. And so you have a distribution table like this, where you have in the numbers column the actual numbers of observations, and in the far right column the probability that something would exist, like 10 out of 100 or 0.1. Or you could look at it from a chart standpoint, where this is what the distribution would look like. It doesn't mean that you haven't got numbers. You can't see what those actual numbers are. See, there's the numbers. 10, 20, 30, 30, and 10. You don't have that here. What you do have is percentages, in this case 0.2 or 20 out of 100. And you can guess, knowing that there are 100 observations, you can guess that the 0.3s up there represent 30 people. But we have graphically represented it versus a numbers table here. We've graphically represented it here. And yet this is still a good representation. And you can see from a picture standpoint, a graphics standpoint, what this looks like, and make some observations about the distribution of all that data. You also have a continuous random variable distribution like this. And you may be looking at only that part that is in the green underneath the bell curve and making observations about it, even though you know that there are observations all throughout the bell curve. But what may be of most interest to you is, well, in this case, the observations between 5.22 and 5.26 on this graph. This is a graphic representation. And if you had more continuous variables instead of discrete variables like this, you can see that with a large enough sample size, you would actually get something that looked more like this rather than the chunky version that you get here. Okay, so a normal distribution is going to follow this format here, and you can create this formula to see what the density function is. But you can graphically represent similar distributions, even though the mu or the mean is different between each of them. Note that while the distribution is the same with the observations, in the top bar you have a mean of 50, in the middle bar a mean of 40, and in the bottom bar a mean of 60. And so you would take a look at standard deviations that approach similarity there, whereas the actual numbers that are being observed are very different. Or you could find distributions where they all have the same mean, but because they have different standard deviations, you are going to see a different representation on that curve. Now, this is still a bell curve, in that you've got the mean there, and it looks very similar on either side. It's kind of like a mirror image. And in reality, most distributions are not like this. They're a little bit different. They may not be skewed, and we got into skewed when you were looking at your earlier statistics class, where you have a lot on one side, a lot of observations on one side and fewer on the other side. But because of the size of numbers, you might have a mean that was not the same as the actual number. It did not split the distribution 50-50. You just happen to have, in other words, the same. You did not have the same look to the curve on the left side as you would on the right side. Okay, so they don't look the same, and that happens, and that's not that that's a bad set of data. It's just things happen that way, but it's not called a normal distribution. You'd have a more skewed distribution that way. So if you were looking at it, I'm going to flip to this one real quick, but let's go back to these numbers. If you're looking at it, typically a normal distribution of numbers, one standard deviation out gives you about 1/3 of all observations on each side. 1/3, or in this case 68% instead of 66, 67%. 68% of all values within one standard deviation, 95% within two standard deviations, and then almost all within 3 standard deviations. And in reality, when you look at it, most distributions are going to have everything within 3 standard deviations. But there will be sometimes an outlier out there. And this is kind of what we're looking at, okay, from a graphical standpoint. That there in the center on the top left graph represents 1 standard deviation, and about 2/3 of all observations are there. 95% in the second one, and almost 100% of all observations are within 3 standard deviations of the mean. Folks, it's been good. Take care.